Welcome to Electronic, where we experiment, learn, and build with electronics. Today's discussion will focus mainly on operational amplifiers. Later on this video, we will be constructing an inverting operational amplifier circuit and study its technical characteristics. Now, operational amplifiers actually show up in far more places than just audio and signal amplifiers. They can be considered as quiet workhorses found inside filters, sensors, control systems, and even everyday household electronics. Some of its most desirable technical characteristics are as follows. First, it has a high input impedance. What does this mean? It does not disturb the signal source, making it less prone to noise. Second, it has a low output impedance, which means it can drive many loads. It also has a high gain. Why is this so? Because it has a flexible feedback mechanism. And lastly, its simple configuration. An operational amplifier is normally implemented using a single integrated circuit. And this one-chip single integrated circuit can actually perform dozens of functions. The op-amp or operational amplifier we will be using today is what is known as a general purpose operational amplifier or op-amp. In the schematic diagram, it would look something like this. The operational amplifier or op-amp is represented by a triangle with 5 pins sticking out of it. Now, the 5 pins are as follows. Here on the left side are the inputs. As you can see here, there are 2 inputs. One is non-inverting, represented by a plus sign, and the other one is an inverting input, which is represented by a minus sign. On the right side here, we have the output, a single output. And the remaining 2 pins are as follows. These are the supply voltages to the op-amp. So one is a positive supply voltage and the other one is a negative supply voltage. The actual operational amplifier, general purpose operational amplifier, is actually an integrated circuit that looks like this. The integrated circuit number is 741. Sometimes it's LM741, sometimes it's UA741. Regardless of the first 2 letters at the beginning, the integrated circuit would look the same. It would have 4 pins on the left and 4 pins on the right. Now, the numbering of the pins are as follows. Now, this is what is known as a dual inline package integrated circuit or a DIP integrated circuit. Normally, it will have 8 pins. The numbering is done like this. You would need to find this circle which marks pin number 1 of the circuit or the integrated circuit. Now, that circle is normally near a half moon notch on one side of the integrated circuit. Once you find that circle and that half moon notch, the numbering of the pins are as follows. Starting from the upper left, that's pin number 1. So if there are 4 pins on the left side of the integrated circuit, so you have number 1 at the top, then 2, 3, 4 going down. On the right side, the pin numbers starts from the bottom. So the bottom right pin is pin number 5. So it's going to be 5, 6, 7, 8 in the right side going up, from bottom going up. Most dual inline package integrated circuits would have the same type of numbering. So the LM741 has that. The LM358, the comparator, same thing. And also for the 555 timer, same format. Now, the internal construction of the LM741 looks like this. Now, you can see here inside the diagrammatic representation of our operational amplifier, the general purpose operational amplifier. The inverting input is on pin number 2. The non-inverting input is on pin number 3. The negative supply pin is pin number 4. The positive supply pin is pin number 7. And the output is in pin number 6. It might be worthwhile to take note here that pin number 1, pin number 5, and pin number 8 is not being used. Actually, in some special circuits, you might have to use pin number 1 and pin number 5. However, pin number 8 is never used. So we're actually only using 7 pins. However, for our demo today, we will not be using 1, 5, and 8. We will just be using 5 of the pins of the integrated circuit. The schematic diagram of the inverting operational amplifier circuit we will be constructing today would look like this. Now, as you can see here, we have the operational amplifier here on the right side with the pins numbered as follows. Now, pin number 3, which is our non-inverting input, will be connected to ground. Pin number 2, our inverting input, will be connected to a resistor, which we will call as the input resistor. We will use a 100 kilo ohm resistor for this purpose. And that resistor will be connected to a capacitor, a 10 microfarad capacitor. Now, also take note that the capacitor has a polarity. We're going to take note of the polarity of the capacitor for this circuit. So the input resistor will be connected to the negative terminal of the capacitor, and the positive terminal of the same capacitor, that 10 microfarad capacitor, will be the one connected to the function generator. Now, on pin 4 and pin 7, which is the negative supply pin and the positive supply pin of the operational amplifier, respectively, will be connected to a negative 15 volt source and a positive 15 volt source, respectively. If you could remember from our Com3 Lab protoboard, we have both of these voltages, a negative 15 volt voltage and a positive 15 volt source, available on the fixed DC supply source section of the Com3 Lab board. The output pin, pin number 6, of our operational amplifier, or our 741 circuit, integrated circuit, will be connected to a 1 mega ohm resistor. This resistor we will call as the feedback resistor. The other side of that feedback resistor will be connected to pin number 2. Now, we will set the function generator for this circuit to output an alternating sine wave, maybe with a 1 volt peak-to-peak amplitude and a frequency where we could actually use 1 kilohertz or 2 kilohertz. It would not matter that much. So a 1 volt peak-to-peak amplitude and maybe a 1 kilohertz frequency. Now, given that what we have here is an amplifier circuit, we should expect that the input signal here on the function generator will get amplified here at the output. The output of our amplifier is on pin number 6. So if I connect an oscilloscope to pin number 6 and compare the output waveforms of the function generator with that of what I will get on pin number 6, I should expect an amplified version of this input signal coming from the function generator. Just how much is the gain? That can actually be computed. For an operational amplifier or an inverting operational amplifier, the gain is actually controlled by these resistors, the feedback resistor and the input resistor, and is computed as follows. Gain is equal to the ratio of the feedback resistor over the input resistor. The negative sign here is not actually a numeric value. It just represents output inversion. What exactly is output inversion? That will be easier explained once we go into the actual demo. So if you would compute the gain here in this circuit, it would look like this. So feedback resistor is 1 mega ohm. Input resistor is 100 kilo ohms. So remember that mega, that capital M, and kilo, the small letter k, on the value of the feedback and the input resistor are also numerical values. So I have to represent that here in my formula. Mega is times 10 to the 6th power. Kilo is times 10 to the 3rd power. So I have 1 mega ohm here, and I've got 100 kilo ohm here. So the ratio of these two numbers will give me a value of 10. Now, notice I did not write minus 10, I just wrote 10 to represent the actual gain in this operational amplifier circuit. In some books, you might see minus 10 to represent the output inversion also on the answer. In my case, it's just a matter of preference. I will just write the negative sign on the formula to represent the output inversion. However, on my final answer, I'm just going to write it as a normal number without the negative sign.
Just like in our previous videos, we will again be using this Country Lab protoboard to construct our circuit. The LM741 integrated circuit, I have it here in my hands. Now, the notch or the half moon notch, I don't know if you can see it, somewhere there at the top here. It's at the top. So if the notch is there at the top, okay, notch there at the top, pin 1 will be here at the upper left-hand side. Then going down from the left, from the top, is 2, 3, and 4. Pin 5 will be here, bottom right, and 6, 7, and 8 will be going up. This is 6, this is 7, this is 8. Now what I will do, I will connect the LM741 to the breadboard in that manner, wherein the notch is facing here on the left side. Now, my advice is this. Try to find a place on the board wherein the IC or your 741 will snug fit. Because if the IC or the 741 is loose, okay, there are a lot of places here anyway. If the IC is loose, you will not get any output waveform. So you put the 741 or the integrated circuit, okay, on the gaps here. So you have two on this board. One is here, the other one is here. Don't use the one in the middle here. It's going to be some problems if you put it there, okay? The IC will surely be loose, okay? So either you put it here down or you put it there up. So try to find the place on the board where the IC would be snug fit, where it's a little bit difficult for you to pull it, okay? Now, let me try to find the place now on the board for this one. Maybe somewhere here would be fine. Push it there. Okay, so as I've said earlier, the notch of the IC, let me just focus that one a little, okay? The notch of the IC is here on the left-hand side, which means pin 1 is here, down, pin 1, pin 2, pin 3, pin 4. Then pin 5 is there at the top, pin 5, pin 6, pin 7, pin 8. Okay? Now, let us now connect the other components you'll be needing on the circuit. Like for instance, okay, we need the on pin number 6 on the output, we need a 1 mega ohm resistor, which I have here. A 1 mega ohm resistor on the output here. How do I know? Again, color code. So the 1 mega ohm resistor is connected in this manner. You got the output on pin number 6, one of the legs on pin number 6, like so. Just connect it like that. Pin number 6, there. Okay. And using a jumper wire, okay, I will tap a jumper wire from here on the second leg going to pin number 2. Like that. Okay, just like in the circuit. There. Going to pin number 2. Now, that's our feedback resistor. Now, the input resistor is here. This is our 100 kilo ohm input resistor. Again, how do I know? You have to take a look at the colors on the body of the resistor. I would like to again refer you to the resistor color code video I have on the channel for reference. Now, for this resistor, okay, I need to connect this one to the inverting input here, down. Connect it here, pin number 2. I'll put the other pin maybe somewhere here at the top, okay? And the other leg of that resistor, this one, this leg, I'll connect it to a capacitor, this one, an electrolytic capacitor. Now, if you can remember on the schematic diagram on the video, the capacitor, this one, electrolytic capacitor, carries a polarity, wherein the positive leg and the negative leg needs to be identified. Now here, in the electrolytic capacitor, this is a 10 microfarad electrolytic capacitor, by the way. The negative terminal is the shorter leg. The longer leg is our positive. So what happens here, on the resistor, we need to connect the shorter leg, the negative, based on the schematic diagram. Shorter leg to the negative, like that. I'll connect the positive on the other side of the, so, like that. Shorter leg to the positive, to the resistor, connect, okay? And the positive, let me connect the positive using a jumper wire, one of jumper wire. I'll connect it to the power rail here down. I'm going to use the red power rail down there. So since I connected this one to the red power to a red power rail down, I would need to connect now the out pin of my oscilloscope to the same power rail as indicated on the schematic diagram. Let me take one. I'm going to use a red power cable, and I'm going to connect it to the red side because I would need that positive terminal of the capacitor, or I'm sorry, yeah, the positive terminal of the capacitor to be connected to the positive terminal of my function generator. Now, pin number three of the IC of the integrated circuit here, pin number 3 needs to be grounded. That's our non-inverting input. So the non-inverting input, pin number 3, I'll ground it. We put it here, jumper wire, using a jumper wire. So to ground it, I'm gonna put the jumper wire here. I'm gonna put it here on the, because it's closer here, on the bottom blue rail. And since that is ground, I will connect another power cable coming from the ground here, ground pin of the function generator, to that line, the blue line at the bottom, like so. Oops, okay, there. Power, okay, ground here. Now, what's now left is the positive and negative power supply pins for our 741 IC, which will come from here, 15 volts and negative 15 volts. Now, based on the pin out on the schematic diagram we saw earlier, positive 15 will connect to pin 7. Let me connect to pin 7. Here, pin 7, and negative 15 will connect to pin number 4. Pin number 4. Here, the other side, there, pin number 4. Yeah, closer look if you want, you see from here, pin number 4, pin number 7, pin 6, jumper wire going back to pin 2. You get the 100 kilo ohm resistor here. This is your input resistor. Here's your capacitor connected to that leg of the input resistor. Okay. Now, we also need to connect the ground of that power supply, the fixed power supply here. There's also a ground connection here to the same ground terminal where we connected the ground of the function generator, which is here on the blue power rail at the bottom. So I'm going to connect it on the same line. There. Now, I could actually switch on the circuit right now. However, before I do that, okay, because I need to set also the function generator to the correct setting. Before I do that, let us first connect the oscilloscope wires here at the top. Again, since we'll be needing both channels of the oscilloscope, I will have one wire on Y1, another wire on Y2, and we have a common wire, the ground, here. Now, we all know that the ground here, the ground wire here, the black one, will have to be connected to the same line where the ground are connected, which is here on the bottom blue. Okay, so let me just do that. Okay, so the ground wire, this is the ground wire coming from the oscilloscope, the common pin of the oscilloscope. I'll connect it on the blue line there, the bottom. Same line where the ground of the positive 15, negative 15 power supply and the function generator is connected, which is the blue power rail at the bottom. Now, how about the Y1 and the Y2? connection here at the top. Okay, let's take the Y2 first, okay? We're gonna use the Y2 for the output. So the output of our 741 is pin number 6. So I'm gonna connect Y2 on pin number 6, which is where the output is, okay? So pin number 6, here, the top. Here, pin number 6 for Y2, there. So Y2 will show the output waveform, okay? A closer look at that, you see here, there. Let's move this one. See pin number 6. Same pin where the leg of the, one of the leg of the 1 mega ohm resistor is connected. See? Okay. Now, and lastly, we need to connect also Y1, this one. Y1 is, we're going to use Y1, okay, of the oscilloscope for input. So if that's the input, I'm going to connect it to where the function generator out cable is connected, which is here at the bottom rail, red side, the bottom rail. Let me do that now. Here. So we're here down. There. Input is there. Oops, wait for that. Okay, see here. So the input, okay, or the Y1 is connected to where the output or the positive terminal of the function generator is connected. Y2 is on the output of the 741, which is pin number 6, and the COM of our oscilloscope is connected to where the ground wires of our function generator and DC supply is connected. So what's now left is for me to just switch on the COM3Lab proto board, which I can do from here. Okay, set the function generator to the correct setting. I will use the COM3Lab companion software for that one. And also switch on, and after that, switch on the power supply, the DC power supply from here. Then we could now take a look at the input and output waveforms right after. Let us now go to the COM3Lab companion software, where we will generate the input and output waveforms of the inverting operational amplifier circuit we just constructed. I've already set the function generator of the COM3Lab companion software to the setting mentioned earlier in the video, which is 1 kilohertz frequency, 1 volt peak to peak for the amplitude, and sine wave here. Now, let us now open the oscilloscope of the COM3Lab software from here. Let's have a bigger display for the oscilloscope here. There. Okay, I'll put a check on Y2 here. And let me generate the oscilloscope now. Click preview, and I'll run it here. Okay, let me just make some few adjustments on the horizontal time division setting. Maybe I could use 500 microseconds. There, I think that would be better. Okay. Now let me just set the trigger to Y1, and I'll just put it in one sweep so that the waveform now stops. We have the waveform. Okay, now as you can see in this waveform, we have two waveforms here on the screen. Okay, one is the black one here is the Y1 waveform. That's our input. It's a shorter waveform, and the taller waveform here is our Y2 waveform, or it is our output. It's our output. Based on the setting of our function generator, our Y1 line, which is connected to the positive terminal of our function generator. According to the function generator, the setting is actually 1 volt peak to peak. We could actually verify that from here. Now, let me just take out the display for the Y2 so that we have a clear one here. Oops, sorry. I took out Y1. Okay, let me just leave Y1 alone. Okay, there. Okay, there. Now, we could actually measure that voltage peak to peak value, okay, which was set to 1 volt on the function generator by using the, call this the cursors, the vertical cursors here, okay? So blue cursor, red cursor, what's a value? You could actually subtract from here, okay? Y1 red is the one at the top minus the value of Y1 blue with the one at the bottom. So it's 500 millivolts, see here, minus negative 563 millivolts. That would be around 1.63 volts coming out, 1.063 volts. Okay, so it's very close to 1 volt. Okay, 1 volt peak to peak. Now the output waveform is on, I'm going to put to check on Y2 this time around. Okay, I'll check Y1. Here's the output waveform. Now the output waveform, peak to peak voltage, you can measure from here. Here, one there, same, the blue here at the bottom peak. Okay, now what's the value? Okay, you could subtract it from here. Okay, that's, you see here Y2 red says 5.13 minus Y2 blue, which is negative 5.06. So 5.13 minus negative 5.06 will give you around 10.19 volts. So as you can see from there, from those values, okay, if I take the ratio of the input waveform, which is the black one here, with that of the output waveform there, okay, let's say output waveform over input waveform, I'll come out with the, if I take the ratio, let's say peak to peak voltage output divided by peak to peak voltage input, I will get a number or result. My result would be around 10 point something. Now, the amplification factor of our circuit could actually be computed as feedback resistor all over the value of the input resistor. Feedback resistor is 1 mega ohms. Input resistor was 100 kilo ohms. So that's actually 1 million ohms divided by 100,000 ohms, which also will give you 10. So the results here on the waveform here confirms the amplification factor of the inverting operational amplifier circuit we constructed earlier, which also gives me a 10 amplification factor. The input was amplified 10 times on the output. Now, the term output inversion mentioned earlier, okay, what is that? Now, output inversion is actually clearly seen here on this waveforms here. When the input waveform is on its positive half cycle, the output waveform is in its negative half cycle. And when the input waveform is in its negative half cycle, the output waveform is in its positive half cycle. As you can see there, the output is the inversion of the input. So if the input is positive, the output is negative. If the input is negative, the output is positive. Output is amplified and is also the inverse of what the input waveform is. So we can see here the term output inversion here on the oscilloscope here, the waveforms on the oscilloscope. Now, the phase relationship between the input and output waveforms can also be seen in this screen on this particular display. What's the phase relationship? Now, as reference for phase relationships, which we will put as a unit in degrees, similar to the unit of angles, okay? One full cycle of a sine wave, that will be one positive and one negative half cycle, okay, of a sine wave. One negative alternation, one positive alternation, and one negative alternation, okay? One full cycle is equal to 360 degrees. Now, phase relationship has something to do with the separation of the two waveforms. How far are they separated? These two waveforms are separated by half a cycle. You can see it from here. The blue waveform is going up here, and the black waveform, the input waveform, is going up in this side. So you can see there's half a cycle difference. From here to here, there's half a cycle. So if we use 360 degrees as reference for one full cycle, and the separation is half a cycle, therefore the phase relationship here for our inverting operational amplifier circuit would be half of 360 degrees, which is 100 80 degrees, clearly shown on this oscilloscope display. Now, with that, I would like to conclude the video for today. And as always, I would like to encourage all of you to keep experimenting, keep learning, and I hope to see you next time here in Derektronic.